Hello, my name is Lisa and I'm going to tell you about the recent work together with Robert König on oscillator-to-oscillator codes. I will first tell you what the motivation for this work was and what its message is, and then I will tell you what I mean by threshold and what TQP codes are. After which we will get to the definition of the actual oscillator-to-oscillator codes. And finally, I will present to you our no-go result concerning these codes. Okay. So in the continuous variable setting, Gaussian operations kind of take the role of Clifford operations. So they are usually easy to implement, but they're not sufficient for universal quantum computation. And what is also known is that continuous variable quantum information cannot be protected against naturally occurring noise, actually not even against Gaussian noise, using Gaussian states and operations only. But then, No, Gilbin, and Young proposed some codes which encode one bosonic mode into several bosonic modes using a Gaussian encoding unitary, but with the help of non-Gaussian auxiliary states. So the only non-Gaussian ingredient in these codes are the auxiliary states, which are in a so-called one-mode Gottesman-Kitayf Presskill or GKP code or state. And we will call these codes oscillator-to-oscillator codes. And we were then wondering whether these codes could be useful for quantum fault tolerance, in the sense that they exhibit a threshold and therefore somehow can circumvent these Gaussian no-go theorems. And we got to the conclusion that the codes that one gets do exhibit some error suppression capability, as No, Gilbin, and Young showed already in their work, but for a physically meaningful encoding, they do not exhibit a threshold. So they're useful, but not as powerful as one might have wished. Okay, but let us first have a look at qubit-to-qubit encodings. The picture that you see here depicts a typical situation in quantum error correction. You have k qubits in a state row, which you want to encode into n qubits using the encoding unitary U. So the code space is a subspace of C2 tensor n of dimension 2 to the k. And then after the encoding, the n qubits are subject to some noise process, which we assume to be identical for each qubit here. And to get rid of this noise, we afterwards apply a recovery map, which typically maps back to the code space. So the whole circuit in the picture can be written in terms of the expression on the bottom, which is equivalent to the expression appearing on the right-hand side, which corresponds to the circuit now appearing on the top on the right-hand side. And this is just due to the fact that R maps back to the code space, because this means that the resulting state after decoding is the noiseless encoding of some k-qubit state, but not necessarily of rho anymore. Now, this whole procedure, of course, is only beneficial if the logical noise strength is smaller than the physical noise strength, because otherwise we could just leave rho unencoded. And here, the noise strength can be measured, for example, by the diamond norm of the distance between the error channel and the identity. So now, similarly, we may also have a whole family of codes indexed by some set lambda, which, for example, corresponds to the number of physical qubits, and which each encode k qubits and have a corresponding encoding unitary and recovery map. And for example, if the n really corresponds to the number of physical qubits, then this just means that we change the number of auxiliary qubits. And so now we say that such a family has a threshold if we can make the logical noise strength arbitrarily small by adjusting the parameter n given that the physical noise strength was below some threshold value delta 0 bigger than 0. Okay, so let's now get to the second kind of encodings, namely qubits into bosonic modes. And here we consider a system of n modes living in the Hilbert space L2R tensor n. And we denote by qi, pi the quadratures, so the position and the momentum corresponding to the ith mode. And we gather them in this vector r. So now the commutation relations can be written in terms of the matrix J, which is defined like this. And also the displacement operators can be written in terms of this mode vector R and the matrix J. And these displacements translate the mode vector R via conjugation by the amount xi in phase space. And the combination of two such displacements is proportional to a displacement with respect to the sum of the corresponding vectors. And therefore, we can write their commutation relations as given. And in particular, two displacements commute whenever the symplectic inner product of their corresponding vectors is an integer. And we also say that xi and eta are symplectically integral in that case. So now Gottesman-Kitaev Preskill or GKP codes are defined as follows. We take 2n linearly independent vectors in R2n, which are pairwise symplectically integral. So we have 2n commuting displacement operators, and we set the code space to be the simultaneous +1 eigenspace of these displacement operators. So to be accurate, the elements of this space are actually not states, but distributions. But for the purpose of this talk, I will just pretend that they are states, and I refer you to the paper by Buzuina and Dubieva for a more rigorous treatment of these objects. Okay, so now the stabilizer group of these codes, so the group of operators that leave the code states invariant, is therefore given by the combination of all these displacements with respect to the vectors xij. But as we have seen on the last slide, the combination of two displacements is proportional to a displacement with respect to the sum of the corresponding vectors. And therefore, our stabilizer group can as well be described as the set of displacements with respect to integer linear combinations of the xij's, or in other words, with respect to vectors of the lattice L given here. Okay, so this lattice has a dual which is generated by eta j such that the symplectic inner product with the xi k is 1 exactly when j equals k and 0 otherwise. And with the help of this dual lattice, we can now get a complete family of logical operators, of inequivalent logical operators, indexed by L per modulo L. And also, the dimension of the code is given by the square root of the relative volume of the unit cells of the lattice and of its dual. Okay, so let us have a look at an example. The standard example of a GKP code corresponds to one mode and a square lattice of spacing 2 times square root of pi. So the displacements, the stabilizer displacements correspond to vectors in this lattice L, which is denoted by L1 in the picture and marked with dashed black lines. And the dual in this case is also a square lattice with half of the spacing and is marked in blue in the picture. And the logical operators, which correspond to L per modulo L, are generated by the two given displacements, which act as logical Pauli X and Z respectively on the code space. Also, the dimension of this code is 2 because the unit cell of L1 has volume 4 pi and that of its dual has volume pi. So dividing them and taking the square root gives 2. And this in particular means that with this code we can encode 1 qubit into 1 mode. And also depicted in the picture is the Voronoi cell with blue edges of the dual lattice, which will be relevant for decoding and which is just the set of points closer to the origin than to any other point of the dual lattice. So for error recovery, let's have a look at the general TKP code again. So QTKP. And here the input for our encoding circuit is, or recovery circuit is a qubit state psi, which is encoded into a logical state psi bar in the code space, which is now stabilized by the stabilizer displacements d psi j. Then after the encoding, we again have a physical noise process, which we assume to be identical for every mode, and for a single mode, it is a random Gaussian displacement noise. So the overall error in this case can also be described by a displacement with respect to a vector which is following a centered normal distribution with variance sigma squared. Okay, so now error correction proceeds as usual by measuring the stabilizer operators to get a syndrome. And since in our case the stabilizer operators are of the form exponential of I times some operator, measuring them is the same as measuring these operators modulo 2 pi. And because they're also of the form 2 pi times the symplectic inner product of psi j with the vector of mode operators r, this says that this is equivalent to measuring the mode operators in R modulo the dual lattice. So what we get is a syndrome in the Voronoi cell of the dual lattice. Next, we compute a correction vector from the syndrome according to your favorite strategy. And then we apply the displacement with respect to this correction vector. So the overall resulting or effective error is then the combination of the displacement with respect to the error vector y and the displacement with respect to the correction vector. So, and this, as we have seen before, is proportional to the displacement with respect to the sum of the error vector and the correction vector. And an important example for the choice of the vector c is the one that corresponds to maximum likelihood error decoding, and is also the one that we will consider throughout this talk. And there one aims to find the most likely error to have caused the syndrome given the error distribution. And we then take c to be minus this most likely error or error vector. Okay. Let's now get to oscillator-to-oscillator codes. Oscillator-to-oscillator codes, as introduced by Knoll, Gilvin, and Young, are defined as follows. Namely, we have k logical modes in a state psi and n minus k auxiliary modes, each in the canonical one-mode TKP state. And this one-mode TKP state is a special case of a TKP code, which is stabilized by displacements with respect to the square lattice spaced by square root of 2 pi. And the dual of this lattice is actually just the lattice itself. So the dimension of this code is 1, which means that it is not an actual stabilizer code because it cannot even encode 1 qubit. So it's rather a stabilizer state. So now, an oscillator-to-oscillator code encoding k logical bosonic modes into n physical modes is defined by a Gaussian encoding unitary US, which in turn is determined by a symplectic matrix S via its action on the mode operators. Okay. So now for error recovery, we see that the encoded state, psi bar, is now stabilized by the displacements of the auxiliary modes, but transformed with respect to the encoding unitary US. And for the noise model, we assume, as in the case of pure TKP noise, IID random Gaussian displacement noise with variance sigma squared. So now also error correction proceeds similarly to the pure TKP case. Namely, we recall that in the TKP case, we measured the mode operators modulo the dual lattice. And here we do the same, just that we only take those mode operators corresponding to the auxiliary modes, and more precisely their transformed version. And as I said, the dual lattice is equal to the lattice itself. And then the other two steps are the same as before. And here, as I already mentioned, we focus on maximum likelihood error decoding, which singles out the most likely error to have caused the syndrome S given the error distribution. So now the question is, as we have seen, the encoding unitary for these codes, for the oscillator-to-oscillator codes, is a Gaussian, and the only non-Gaussian ingredient are the auxiliary states. And the question that now arises is, can these codes circumvent the no-go theorems for Gaussian error correction? But as we will see, also oscillator-to-oscillator codes have their limits. And to see this, we studied the recoverability of these codes under random Gaussian displacement noise and maximum likelihood error decoding. And as in the qubit case, we are ultimately interested in the resulting or effective error channel, which in this case is again a displacement error channel acting on the logical modes and which can be described by the random vector x, which corresponds to the distribution of the displacements. And now for a fixed epsilon bigger than 0, we say that the decoding was successful if the resulting error lies in a epsilon ball around 0 in R2K. And then our main result tells us that the decoding success probability is bounded from above by the probability mass of, or with respect to a standard Gaussian, of a ball around 0, whose radius is determined by epsilon, the standard deviation sigma of the physical noise, and the squeezing of the encoding unitary. And in particular, we note that this bound does not depend on the number of physical modes. And this means that just employing more auxiliary modes does not help you to get rid of this bound. So here, the squeezing of S is equal to the maximum symplectic eigenvalue of S, and it corresponds to the maximum amount of squeezing required for any mode when implementing the encoding unitary US. And for a passive Gaussian unitary, which preserves the energy, the squeezing just equals 1. And in that case, the unitary can be implemented using beam splitters and phase shifters only. And these are typically readily available operations from linear optics. But as soon as the squeezing gets non-trivial, one has to use operations from nonlinear optics. And the implementation of the unitary corresponding to this symplectic matrix gets even more challenging for larger squeezing. But now our bound tells us that the decoding success probability can only be high if the ball around 0 includes a 2k dimensional centered normal vector whose norm is close to square root of 2k with high probability. And this in turn means that the squeezing needs to grow like square root of 2k over epsilon. And this, of course, diverges for epsilon going to 0. So as a consequence, oscillator-to-oscillator codes do not have a threshold for physically meaningful, that is, bounded amount of squeezing. So one thing to mention here is that this result is, of course, established for maximum likelihood error decoding, as I said. So this decoding aims to find the most likely error given that corresponds or fits with the error syndrome given the error distribution. But we cannot exclude the possibility that other decoding strategies, in particular maximum likelihood error coset decoding, could possibly yield better results. And this decoder differs from the one that we consider here by that it does not find the most likely error itself, but the most likely error coset modulo stabilizer operations. And it could possibly outperform our decoder, but it also involves coset probabilities, which are typically hard to compute. Okay, so now in order to get this bound, what we use is that our problem can be reformulated as a purely classical estimation problem, which we call here partial informed unwrapping of modulo reduced Gaussian vectors. And it will be clear in a second why we chose such a complicated name. So for the classical problem, we have a parameter delta and a vector in Rn, which is split into a part A and a part B, a covariance matrix, and we denote by xb star the modulo reduced version of the B part of the vector x with respect to the parameter delta. And then for a normal distributed vector x with covariance matrix sigma, classical problem is as follows. Given the modulo reduced version of the B part, we want to output an estimate of the A part. And this is a variant of the well-studied classical problem, which is called informed unwrapping of modulo reduced Gaussian vectors, which aims to reconstruct a random Gaussian vector from its modulo reduced version. And here the informed just corresponds to that the decoder knows the covariance matrix sigma. Okay, and the strategy that we use here, of course, corresponds to the maximum likelihood error decoding. And here it finds the most likely vector fitting the modulo reduced B part, and then one just takes the A part of this vector as estimate for the actual A part. Okay, so now the following lemma tells us that the success probability of the classical problem, which is equal to the probability of the estimate being epsilon close to the actual XA, is given by the given expression. And here, the V is the Voronoi cell of the degenerate lattice determined by sigma to the -1/2. B epsilon of 0 is the closed epsilon ball around 0 in Rk, and can be seen as an epsilon thickening of the first k directions. And delta set n minus k corresponds to translations by lattice vectors of an n minus k dimensional lattice of spacing delta. And this this lemma can actually be readily applied to our original problem, because the success probability of the classical problem equals the success probability of the original problem if we set the parameters k and n to 2k and 2n, delta to square root of 2 pi, and sigma to sigma squared sts to the minus 1. And here the S is the symplectic matrix corresponding to the encoding unitary US. Okay, so this lemma tells us that in order to compute the success probability, we have to compute an integral over a Gaussian density function over a union of displaced epsilon thickened degenerate Voronoi cells. And these Voronoi cells can be either seen as the intersection of uncountably many half spaces, or as the intersection of countably many sets bounded by surfaces defined by quadratic forms. But neither of these options is really handy for the integration that we want to perform. But luckily, we can also show that each of these Voronoi cells is bounded by a polytope of dimension n minus k. And with an appropriate parameterization of these polytopes, we can show that for a centered random distributed vector x with covariance matrix sigma, the success probability of the classical problem is bounded by a sum of integrals given on the right-hand side. And now for these integrals, these we can now bound using standard techniques. And here, the blue part is the probability of xa belonging to a shifted ball, given that xp is equal to psi. And here the lambda hat is a function of the covariance matrix sigma. And this expression then can be bounded by a Gaussian measure of a ball around 0 by using Anderson's inequality. And now, since the remaining part can be written as a single integral over a probability density function, which is of course bounded by 1, we can bound the whole success probability itself by this Gaussian measure of a ball around 0. Now you see this expression already looks pretty similar to what I've showed you in the main result, and actually getting to this desired expression just requires some massages of this measure. Okay, so as a conclusion, oscillator-to-oscillator codes require an unbounded amount of squeezing in the encoding unitary to get a threshold when maximum likelihood error decoding is used, but they may nevertheless be useful for error reduction, as shown by No, Girvin, and Young. Okay, so then thank you for your attention, and bye.